Programming Throwdown, episode 147, Quantum Computing with Yonatan Cohen. Take it away, Patrick.
Hey everyone, welcome to another episode. Today, I'm excited to be able to have someone to talk to about quantum computing. This is something even dating back many years that I've been intrigued about. I've read various superficial descriptions of, but never really been able to go in depth about with quantum computing. And I'm excited that we're here today with Yonatan Cohen, co-founder and CTO of Quantum Machines. Welcome to Programming Throwdown.
Hi, it's great to be here. Thank you for inviting me.
Awesome. Well, we normally get started by a little bit of an introduction about yourself, how you got into technology. Some people have like that one time they remember that, maybe their parents brought home a computer or they went to school and the Oregon Trail was put in on a floppy disk. Do you sort of remember your first exposure to computers or technology?
To computers in general, yes. I did get a computer at a very early stage. And I was also very interested in physics, in fundamental physics, since I was very young. But really, I got into quantum computing when I was at university. So I did my bachelor degree at the University of Washington in Seattle. And I had a great teacher. So it's all about teachers, So he's a professor at University of Washington. His name is Boris Blinov. And he was this great guy, and he was teaching quantum mechanics 101. And that kind of blew my mind because it kind of connects computing and fundamental physics, which are two topics that I truly loved from a very early age. And that kind of brought things together for me. And since then, I'm hooked on this subject.
Oh, nice. It's interesting. There's actually a lot of people we talk to who kind of have this physics, computer science, hybrid, kind of crossover. I guess the ways of thinking maybe are same. I mean, there's the obvious computers use physics to work, but I feel still there's a lot of crossover there. That's a pretty common background.
Right. I mean, it's interesting because, the reason I went to physics and not to computer. So when I was very young, I was obsessed with. So how does a computer work? When you're a kid, why do I see those things on the screen? Yeah, how does it all works? And then I took a few courses, and at some point, I was obsessed also with how the universe works. Why do I see all these things around me? So it's kind of like the same thing, just replace everything that you see around you and the screen of the computer. So apparently, it's I think it's easier to understand how computers work than how the universe works. So I felt
we're going to go deep right out the beginning.
Yeah, so sometimes during high school, I realized, okay, yeah, I think I understand how a computer works, so I better just go in the physics direction. But once I learned about quantum computing, I think it's interesting because I think that quantum computing is really so some of it is about what's possible to compute, just to compute in, with certain amount of time, a certain amount of resources. And that sort of goes back into the kind of fundamental how the universe works thing, for me.
Oh man, are we going to ask that question? Are we all in a simulation? Is it? Are we headed to this?
Point,
we're just going to tee it up right at the beginning.
For sure. I don't know if it's simulation, but you could view, the laws of physics as kind of some kind of a very sophisticated program, and you can ask what are the rules of programming. And these are the rules of physics, right? And quantum computing builds on that. And another interesting thing is that there are a lot of interesting thinkings right now, which might be the first applications of quantum computers as to how quantum computers can allow us also to understand deep concepts in physics. So now it's going back, the direction goes back, and maybe these computers can help us understand fundamental physics better.
Wow. Oh, that's cool. Yeah, it's interesting sometimes how those things go in cycles and iterations, and sort of one helps the other helps back, and it sort of it's kind of fun that way to see those cycles happen.
Yeah. Sorry to jump into the philosophy of quantum right away. Yeah.
We're just gonna roll with it. So what I'm gonna say is I think a lot of people maybe have those questions that you're saying. Like I think, and a lot of people listening to this podcast are self-selecting as potentially the people who ask those questions. But I don't know that everyone pursues the answers with the same, sort of vigor, or you can't pursue every question you have equally, right? Like you would just get nowhere, just navel gaze, right? So like, but I think a lot of people have that. So how for you did you go from like probably a relatively common question of, why is my screen lighting up to, or how is my computer choosing these pixels to like, actually going in and starting to learn physics and quantum mechanics and then rolling that into choosing that to be a career? Do you feel like you sort of, was that an intentional thing? Did you sort of like fall into it? Was it just pursuit of those questions?
Well, sort of. I mean, I believe that you kind of roll in life, so it wasn't really. I don't see it as a single choice, but I think things lead to one another. So I was very interested in physics. I went to study physics, and then once I was exposed, as I said, to quantum computing, I felt that this is really a way to look at fundamental physics in a kind of eye-opening way. But then I actually went and did my PhD, which was in condensed matter physics, which is related to quantum computing, but not exactly. And in parallel, at some point, I also, together with my partner, who's today the CEO of the company, we wanted to be entrepreneurs. So we felt like we got to understand that as well. How do you start a business around technology? And one thing led to another. And then, we realized that the only thing that we really know is quantum stuff. So that led to starting a company in quantum computing, and that's what really got me into choosing it as a career path.
Well, I feel like when most people say I'm going to make a startup, they mean like I'm going to make a website. Like I'm going to go and I'm going to download a lamp stack, and maybe even today I'll run it on AWS. A lot easier today. And I again, a lot of people probably have that entrepreneurial. Maybe I could do this. Maybe I can make an app or a website. But you said, well, the thing that I know best, I'm going to go start a quantum computing like startup. Like I don't like help me understand that. That feels like such a big leap. Maybe like saying condensed matter physics as like a PhD. Maybe that's the thing I'm missing. I didn't go that route. But like help me understand, how does that, is that something you felt that there were like particular problems you knew that needed to be solved? Like how did you kind of decide that that was going to be a successful endeavor?
Well, it's an interesting story. So basically, it's never like a straight line, right? So we knew we wanted to start a company. In fact, we didn't start from quantum computing. To be honest, we had lots of ideas, machine learning, like the usual stuff, as you said. But at some point, well, we realized we realized two things. First of all, it was about 5 years ago when the quantum industry started to evolve. And then there were a few things that happened in the quantum community that kind of got us thinking, oh, well, quantum is really starting to happen. Something is happening. So, and really at the same time, we realized, hey, this is really the only thing that we know. Like we don't really know how to build the best website.
That's never stopped anyone before.
That's true. But yeah, we realized this is our expertise. We still didn't know what we wanted to do in quantum, and that's when we called our third co-founder, who's the chief engineer of the company, who did his postdoc at Yale University in one of the top quantum computing groups in the world. And that's when we kind of started sitting together, the three of us, and thinking, what do we want to do? So Nissim, who went to Yale, also was the first person in history actually to perform the first experiment that demonstrated what's called quantum error correction. So Nissim was the first author on a paper that is really one of the biggest milestones, I would say, I don't know, in the last, let's say, decade in the field, because quantum error correction is the kind of like mainstream way that the community believes that we should take in order to scale up quantum computers, build truly large scale full stack quantum computers. So Nissim did that, and then we were sitting together and thinking, what are we going to do? And some of the things that were required to do this experiment were things that we felt are really bottlenecking the field. That's what's called so when you look at a quantum computer, it's built out of layers. There is the quantum hardware, and then there is the classical hardware that talks to the quantum hardware, and then there is the software. And the classical hardware that talks to the quantum hardware is not quantum, but it's very complicated classical hardware that needs to be specially designed to talk to the quantum hardware. And we felt that everybody's working on the quantum hardware, but there are many bottlenecks, especially if we look at 2, 3, 5 years, 10 years from now, in this classical hardware, what's called the control system also. So we realized that's where we want to focus on, and that's what we did.
Awesome. Maybe to roll it back a bit, I guess, like you're saying, I have this feeling too, not as being anywhere near the field, but the number of articles that make sort of mainstream media, so and so company has X number qubit new record, or had a quantum entanglement for X time, or all of these things I feel are coming out, more and more frequently, where people are beginning to say, hey, maybe we're on the cusp of this. I don't want to say like a revolution, but like this fundamental change where now it goes from an experiment to a practical usable thing. And I'd love to get your thoughts on there, but maybe we cue them up for sort of later in the thing. But like maybe rolling it back to, kind of like the beginning, I think like people kind of understand, or maybe they do there was the ENIAC and there were the code breakers in World War II building what I would say leading up to where we are with the computer we're all using right now, the sort of classical computer. The architecture, I think the term would be the von Neumann machine, where you have like a CPU and it has registers and pulls from RAM and processes things in a pipeline. The thing that we all, learn to program when we go to school and learn computer science. But at that same time, like some of those things that unlocked that were coming out of the field of physics, things like vacuum tubes and transistors. And that was around the same time, I think, like when that quantum stuff, I guess for me, it's always those quotes back to Niels Bohr and Albert Einstein. Not that I know anything, but it's like, oh, God doesn't play dice with the universe, right? Like quantum mechanics has to be wrong. I think that might be a bit of a superficial take on his belief about that. But I mean, you hear those arguments about these people that today are sort of shortcut names for people who are smart, right? Einstein, Niels Bohr, like, these are like the father. Like, oh, these are just stereo archetypes of like geniuses, right? Creating these fields. But maybe kind of walk us how we got from like that there is some kind of physics that isn't classical or kind of Newtonian or relativistic like Einstein, but this quantum thing, and how it kind of ended up getting us to where we now kind of fuse these two together, quantum computing. That was a lot. Sorry.
Yeah. No, I think that's one of the most interesting topics to talk about. I mean, so the history of this field is very interesting because, so as you said, I think that quantum mechanics was developed pretty much during the same, several decades where the first concepts in computing were developed, and that was independent. And sometimes in the 80s, these concepts started to come together, which I think is amazing. But if we go back to the beginning of quantum mechanics, so quantum mechanics, what it really tells us is that, okay, so we have this, what we thought, the laws that we believe that the nature obeys. So call it, if we want to talk in programming language, then what can I program? What can I even program? What's possible? And then quantum mechanics, it basically expands it in ways that are a bit weird to grasp when you learn about it, but it actually expands it, I think, in a very elegant mathematical way that makes very complete mathematical structure, maybe more complete, in fact, than classical physics, even though there's still a lot to discover. And then so people, explore that for many years, while at the same time, kind of computers happened. And I think these two, so quantum mechanics, completely revolutionized how we think about nature, while classical computers completely revolutionized our day-to-day lives, right? And what we can do with nature, with the classical nature. And then sometimes in late 70s, beginning of 80s, some people started thinking, okay, these concepts, they're related in some sense. It came from several directions. One was, can I simulate a quantum system using classical computers? And that turns out to be very, very difficult. So if you're trying to simulate certain quantum mechanical systems, it just takes forever on a computer. So you ask, okay, so so nature at least simulates itself very quickly. So why can't I do it with a computer? We have this concept of a Turing machine. That is a machine that's equivalent to all other computation machines, right? but no, I cannot do it with quantum mechanics. So immediately, well, not immediately, it required Richard Feynman, which is one of those people that sound like someone smart. And so he asked this question, okay, so we cannot simulate nature efficiently with classical computers, but he took the next step also, and he asked, so should we build a quantum system that can simulate nature for us? And that is sort of the first concept of a quantum computer. There was also Paul Benioff that was giving talks about the computer as a physical system. Think about the computer as a physical system. What are the fundamental limitations of a computer in terms of generating heat? The fact that classical computers are irreversible. You cannot reverse the computation, while quantum mechanics is actually reversible. Everything that happens in quantum mechanics, you can reverse. So all of these concepts sort of brought people to start thinking about, can we build a machine that is by nature quantum and is a general computation machine? And the first person to actually bring it down to the language of computer science, I think, was Eliezer Deutsch, who proved that there is a concept of a universal quantum computer that could basically simulate any other quantum system, just like kind of a Turing machine does to any other classical system, right? And that sort of just expands all these concepts.
Wow, there's a great tour. There's a couple. I have a lot of questions, but I mean, I think like no, that was awesome overview. One thing that you said, I actually hadn't heard before, but I guess like now I'm trying to puzzle it out in my head, which is I think maybe people don't know, but this thing you mentioned about irreversibility of normal computers, right? I think that when you have, if you think about logic gates, which underpin this, I'm going to try. You can tell me if I get it right or wrong. But like, have like a CPU, and the CPU is composed of logic gates, and if you send two bits into an AND gate, you're an OR gate, 1 and 0, 1 and 1, 0 and 0, and then you get the truth table, what comes out the other side. That having a 1 on the output of an OR gate doesn't tell you what the inputs were. So some amount of information is sort of lost. I think that's related to sort of that Maxwell's demon and this like, oracle allowing, and the information theory, like you're destroying that information. Some of the information is lost because these things aren't reversible. And it tries to set, I guess, a lower bound on the amount of energy it takes to compute certain equations because you have this amount of information lost. And it's not that you can compute it for that. Like it takes way more energy than we are calculating that way to do it. But there's this idea. So maybe folks hadn't heard about that, but I think you get into that if you study computer science and how CPU architectures work and sort of ideas for getting around thermal limits and these kinds of things. But I actually hadn't heard what you were saying, which is quantum computers are reversible. That this idea that actually they don't have that same issue.
Yeah, exactly. So let's start from classical computers. Classical computers have, they have two main building blocks, right? We have the bit, or the bits, that's how we store information. Then we have the gates, which is how we process information, right? And so every program, essentially at the end of the day, fundamentally is a sequence of gates performed on a bunch of bits, right? And as you said, those gates are, the way we do it at least now is, they're irreversible. So we lose information along the way, and that actually generates heat. That goes back to a computer as a physical system. Whenever you lose information, you generate heat. Yes, we are very far away from this limit. By the way, right now, I think we're several orders of magnitude from reaching. So most of the heat that the classical computer generates, by far is not coming from that. But that sets sort of the fundamental limits of how we do currently classical computer, and people, started asking whether you could build classical or quantum systems that are reversible. Now, quantum systems, they work with, they replace the notion of a bit with the notion of a qubit, which is not a system that can be either 0 or 1. It can actually be in both 0 and 1 at the same time with certain weights. We call those amplitudes. So we say it's in a superposition of 0 and 1. It's, I don't know, a little bit in 0 and a lot in 1 and vice versa. In fact, those amplitudes, these waves can also be negative numbers. So it can be minus 0.1 in the 0 state and whatever plus 0.9 in the 1 state. But then you operate on these qubits with quantum gates. And quantum gates, yes, they're always reversible. So we call this unitary transformation. But so every quantum gate has certain number of bits going in, the same number of bits need to go out, and along the entire quantum circuit, every operation is reversible. So, in fact, at the very beginning of the field, people asked this question of whether even a quantum computer could do everything that a classical computer can do because it's reversible. So, that was the first thing to prove that a quantum computer can do everything that a classical computer can do, and it can.
I was going to ask.
The answer is that yes, it can, which also shows you that you could build a reversible machine that's equivalent to a Turing machine. So you could do that, which is a great, I think, a very interesting concept by itself, unrelated to necessarily quantum computing. So you can build a reversible machine that does whatever an irreversible machine does. And then, in addition to that, we can also show that because of the quantum nature, actually, because these amplitudes are not just complex numbers, we can also take advantage of this and do more than a classical machine can do.
So yeah, I have a ton of questions about qubits as well, but actually, oddly, I'm gonna skip those for a second and ask about the gates because I guess like on this journey we talk about logic gates, and most people have seen the picture of an OR and AND gate, or I shouldn't say most people. Hopefully you have. If not, go Google it and you just sort of see the picture. But it's also maybe 15 minutes you could explain someone like doped semiconductors in certain ways and have them reason through how like a higher voltage potential and a lower voltage potential and a third, and how a not works or how an or works or how an and works. So maybe people don't know that. I shouldn't assume, but like, I feel like that's readily accessible. Like I don't have a background in semiconductor physics, but like I have a rough working understanding as a practitioner in the field today that like there are these semiconductors and there's gates and they're doped and they're, how it would take me a long time, but you could sit down and sort of draw gates and figure it out and work your way through it. But when you say that you have a qubit in a superposition and then a quantum computer gate, I just don't even know. Like, is that it? What is that gate? Is it a physical thing? Is it semiconductor? Like, how? Like, what does that actually look like?
Yeah, that's a great question. People don't talk about it enough, so it sounds like so it sounds inside a cloud of fog, but it's actually pretty straightforward. So the way it works, so okay, there are different implementations of qubits today, but most qubits are what I call stationary qubits. So this is a physical system that sits somewhere in space. It could be, for example, an ion or an atom that's trapped with laser beams. So imagine you have a bunch of ions sitting in a row, some vacuum chamber, and these ions are the qubits. Actually, what the 0 and 1 of the qubit are two orbitals in which the electron can be. So I don't know if you remember from high school chemistry, you have an atom, so inside you have an electron, and the electron can be it circles around, but really it can sit on different orbitals, right? It can be on one orbital or the other, but it can also be in a superposition of those orbitals. So this is our qubit. Basically, we take two of these orbitals, and one of them is our 0 and one of them is our 1 state. Okay, so we have two states, and now, as you said, we want to start to apply gates to this system. Now, so that physicists like to shoot laser beams, so we do it as well here. And so we shoot a laser beam here. I actually do it for a reason. So we shoot a laser beam on the ion, and that actually causes the electron to move from one orbital to another. Okay, and if we do it just in the right way, we shape the laser beam correctly, it can also make the electron go into a superposition, and it applies the gate that we want. Okay, so we can apply any quantum gate by different shaping of these laser beams that hit these ions. Okay.
So it has to interact with two though, right? If you're gonna have like not operation on one, or you only perform it on one. Like I guess is it gate here a single qubit and you're applying like how
Yeah.
maybe I lost it, maybe
No,
I
that's a perfect question. So what I described was exactly a single qubit gate,
okay,
which is
okay, okay.
so when you think about it, so think about the qubit. One way to think about the qubit is So a bit is 0 and 1, right? So I can have an arrow that points down or up. Yeah. A qubit is like an arrow that can point anywhere on a surface of a sphere. Okay.
Okay.
So that actually this is an accurate mathematical description. So I could describe the state of the qubit as a point on the sphere. Yeah. So as in contrast to the classical bit, where the only single bit gate that you can perform is a NOT gate, right? Just from 0 to 1 and
Yes.
1 to 0.
Yeah.
A single qubit gate, we have basically infinite number of single qubit gates because we
Oh,
can perform,
interesting.
yeah. So we can perform any rotation on the surface of the sphere, right? So actually, the power of the laser beam, as well as the phase of the laser that we apply to to this qubit, to this electron inside the ion, that's going to determine how fast we are rotating around the sphere, and the phase will determine basically around which axis we're rotating. So then you can really create any rotation on a sphere.
Oh, fascinating.
Yeah. And this is just a single qubit gate. And of course, as you said, now I need to, okay, of course, we want qubits to interact. This is one of the most important things in quantum, because we want to create entanglement. We want to have the entire system go into this like single quantum state. And for that, we need two qubit gates. But that's, it's a similar idea. You hit those ions with some laser beams and you bring them to interaction. So you have to have some physical mechanism in which they interact, but this physical mechanism depends, on external forces like these external magnetic fields, electromagnetic fields, and so on. And this was about ions, but I could do the same with superconducting qubits, which is another leading platform where you create a small circuit from superconducting material like aluminum, for instance. And when you cool it down to very low temperatures, it starts to behave quantum mechanically, and then you actually can create a system which is kind of like the ion. It's a circuit. It's a macroscopic circuit that we can fabricate on a chip, just like you fabricate transistors on a chip. You fabricate it on a chip, but it's like an artificial atom in the sense that it has those energy levels, quantum energy levels, just like the orbitals in the ion. And I could send a microwave. Now it's not a laser pulse, it's a microwave pulse because it's just different energies, but it's the same concept. I shoot a microwave pulse through a wire that's connected to this chip, and this microwave pulse basically hits those qubits, those superconducting qubits, and perform the gates. And I could perform two qubit gates, single qubit gates, and then I could create what's called a universal set of gates, which is a similar concept to the NAND gate in classical computing, which says that from a discrete number of quantum gates, I could actually create a universal quantum computer.
Well, you just built them all for us. I mean, you said a lot of things that are pretty sophisticated. So I don't want to get there quite yet, but I'm seeing your setup about the control systems for this. Lasers and controlling phase and intensities, and I assume frequencies, and like I mean, I think we're gonna. I see where this is headed, but before we go there, you mentioned that there's sort of like superconducting, that there's ion, there's like different approaches. And it sounds like you're saying that it's not clear yet necessarily that one is better. Are there trade-offs that are being explored? Like one is better for this thing, the other is better for this, or it's just everybody's just in a race to build the first one that works?
Yeah, exactly. I mean, we don't have kind of the silicon transistor yet of quantum. So there is a race now between many different kinds of qubits. I'd say there's at least five, six leading candidates to be the kind of dominating qubit. So that's happening right now, and some of them have, yes, advantages in some areas, and some have advantages in other areas. So it's hard to say who's going to win this race. And there could be also combinations. So when you think about a modern computer, actually, there are many different ways in which we implement bits. So some implementations are better to create, a hard drive, and some implementations are better to create the bits that go into the CPU, and so on. So it could be that in the future, we're also going to see some hybrids, quantum computers that are based on different types of qubits.
Yeah, I never thought about it that way, but I guess you're absolutely right. Like an SSD or flash and DRAM and a computer all have like slightly different kind of mechanisms for representing like 0 or 1. So yeah, I guess from that standpoint, yeah, you're absolutely right. And they have trade-offs. It's not that only one is correct. There's a variety of reasons you may choose one or the other.
Right. I can give you an example. For example, so a trap ion system is the lifetimes, or the time that the qubit can actually preserve quantum information are much longer than superconducting qubits. But superconducting qubits are much, much faster. So you can perform the gates about 3 orders of magnitude faster. So, so that's a huge advantage, right? Because I mean, okay, let's say, okay, so it's true that a quantum computer should be, at the end of the day, exponentially faster, and we don't care about those pre-factors. Theorists, they don't care about these pre-factors because it's not fundamentally a part of, whether it's in this computational class or another. But these pre-factors matter. Like if we build the first quantum computers that can actually do something useful, and it can do something that a classical computer does in 10 days, maybe it can do it in 1 day. So that's great. I solve a problem, 10 times faster, but that's on a superconducting qubit computer. On a trapped ion computer, it will take 1,000 days, right? So at least for the first, decade of the field, I think that this is going to be important. But then on the other end, as I said, so maybe some qubits are better for memory and some for computation and so on.
I know you already kind of, I guess, seeded my thoughts there, but the error correcting, so everyone kind of knows, like in a normal, or maybe not, I keep saying everyone knows. I feel like I have been, like, heard it over and over again in a normal computer, like, oh, you can have a cosmic ray comes in and strikes your memory and flips a bit. But we also know, like, electrostatic discharge, or, just like depending on time, something like DRAM needs to be refreshed, or you can have corruption. So I think we tend to not think about errors too much, except when your hard drive gets corrupted. But like you tend not to think about, I guess, errors too much, and it gets handled, and you learn about like CRC checks or hashes, things that are either tell you if there is a problem or tell you how to fix the problem. That's like kind of like the classical computer thing. When you're talking about quantum computers, I assume it's sort of analogous. Is it like lifetime measured in units of time, or a number of operations? Like, what are the things that cause you to sort of, you talk about like very cold temperatures and high vacuum. So I start to think about things like, well, you can't really have it exactly pure. So there's always like something floating around, or you're not exactly cold enough. Is it just system things like that? Or is there like more fundamental things that are creeping in that cause you to kind of error out and not get the thing you thought you were going to get?
No, so yeah, the errors can come from many different mechanisms and sources of noise, as you said. It could come from simply the fact that there is a finite temperature. So, finite temperature tells you that, okay, if you're in this energy state, you could jump to a higher level energy state. Then, so you try to isolate more, to cool down more. As you said, cosmic rays or even photons that wander around could give you errors. And then the control system itself can give you errors as well, because we're not sending exactly the right pulses that we want to send to the system, and there's noise, there's electronic noise coming from the classical electronics, and so on and so forth. So there are many. So I think there isn't exactly a fundamental thing, and I think we could build better and better qubits in the future. I think that's super important to do that. There is, however, a challenge in the fact that on one hand, you want to isolate. So for a system to be quantum and to be protected from the noise from the environment, you want to isolate it from the environment, right? But then on the other end, we do want to speak to it from the control system, right? These laser pulses. So we do want to couple it to the environment. So there is this challenge where on one hand, you want to couple it to the control system, but you want to isolate it from everything else, and even from the control system, you want to isolate it when you're not sending the passes that you're intending to. So it's an engineering problem. I wouldn't say it's a fundamental issue, but it is I think a big challenge that's going to be important. And again, one of the main ways to deal with it is to say, okay, I'm good enough now. Let me just now start doing quantum error correction. and that basically deals with this noise. Because what quantum error correction does, which I think is interesting to note, is that it digitizes the quantum information to some extent. So it's so I talked about this qubit, which is kind of like a vector on a sphere, right? So you think about it, it's an analog system, and one of the things that bother people is that, okay, so how can we build this thing? It's analog. So I can have an error which is a tiny angle that the qubit is not exactly pointing down; it's pointing one angle to the right. So that's a challenge. But quantum error correction actually allows you to digitize those errors. It digitizes the errors. So when you do quantum error correction, you either get an error with a very low probability, or you don't get an error at all. And that's very important because it kind of does what we do with digital. It kind of does what we do with digital electronics, where we are protected from a certain threshold, and then it's very hard to get errors. So you kind of can lower and lower and lower the error rates to as much as you want, basically.
Do those errors creep in? Like you mentioned, the qubits needing to be in superposition, and then they can sort of, I guess, like fall out of superposition during the calculation? Or is it more, I don't know, I don't know if that's the right analogy, but like a measurement thing? Just like when you take a measurement, there's some noise. And so if the thing isn't exactly where you thought it was, and there's just sort of measurement error, or is it, yes, all of the things?
Yeah, so it's both. So when we say that the system falls from a superposition, one of the reasons it falls from a superposition is because it interacts with something in the environment. And in some sense, you can think about it as sort of it's being measured by the environment. So the environment kind of measures the system and sucks the quantumness out of it because it kind of collapses it to one of the states, right? And we don't know to which one. I mean, if we could then measure the environment, maybe we know to which one, so we can fix it. But we don't. So whenever we get coupled to the environment, we kind of get measured by the environment, and that is one reason for the noise. Then you also have errors when you measure the system. Maybe you measure it in the wrong way. So these are called readout errors. So you get all kinds of errors you have to deal with. Yeah.
So we've been talking about, like, I guess the fundamental, sort of like qubits and gates, and I'm not going to ask you to describe sort of like algorithms that you compose from those things, but they exist, as you mentioned. Like you've proven that you have the equivalent of like the fundamental one. So you could just, I guess, as a backstop, build like the naive old way of doing things in the new approach. But you also mentioned this sort of like trying to use them to do, I guess I would kind of take it as like fundamentally quantum approaches to solving problems. And I guess, I mentioned even in the opening, like, hey, we're going to factor large prime numbers. Everyone says, oh, quantum computers are just going to like factor large prime numbers. All encryption is going to be broken, or at least the ones that rely on, prime testing or factorization. But then you mentioned something which I've heard before, but I never really kind of understood, which is actually trying to have the quantum computers simulate quantum computers as like a proof that you're doing like a fundamentally different thing. Could you maybe like dive in like why that matters?
Yeah. So actually, a lot of people in the field nowadays believe that simulating other quantum systems is perhaps are going to be the first applications of a quantum computer, because these are sort of also the easier ones. So we can do those. There are interesting questions to ask about how quantum systems behave that we cannot ask because we cannot simulate quantum systems with many degrees of freedom, that we could probably do with relatively low number of qubits. So maybe a few hundreds of qubits, you can already simulate quantum systems, molecules, like phases in condensed matter, and things that are actually interesting. So at the beginning, I think they're going to be interesting for science, which, by the way, I think I think it's already a good application to start from. Let's build a machine that can help us, not just so. First, quantum computers are exploring themselves, right? Just let can I build this thing? How can I build better? How can I scale it up? Then I think they're going to explore other quantum systems, answer some scientific questions that we have. Then I think those things are going to probably evolve into something that is already of some industrial value. Like I can simulate a molecule, and I can maybe build better drugs, or better nanomaterials, or better materials for all kinds of usages in industry. And in parallel, there is then optimization problems that we hope to get some advantage from quantum computers. And I think those applications like breaking all encryption codes are a little bit more down the road. I think that they just require a lot of qubits and a lot of error corrected qubits. So some of those more, you know, near term quantum simulation applications, I think, also require less quantum error correction and maybe noisier qubits. So
Thank you. That's super eye opening. I guess I have fallen into this trap about like thinking of traveling salesman problem or NP complete problems in general and like quantum computers going and attacking, you know, all those things that are really hard for computers to do today and maybe opening up new avenues. But this thing you mentioned, I guess not my field, so I don't traditionally think about it as a computer field or my computer field, which is eye opening. Like how I guess if I elaborate a bit, like drug modeling or interaction, like how a molecule of a certain shape interacts in your body is insanely hard on computers today. And in fact, like I guess looking at the whatever biotech startup failure rate, apparently if it was easy, they would be doing it. And so that it's not means it must be pretty hard. But you're kind of mentioning that it may be earlier in the quantum computer thing that you can begin to make progress against those sorts of things, which are not really even, I want to say solvable by computers, but not practically solvable by computers today. So they aren't even really I don't know if they're used or not, but aren't sort of like using to sort of fundamentally solve the problem. And so now you're saying maybe quantum computers, things like materials and molecular interaction, those kind of things. That's actually that's encouraging because I always get sad. This thing you say like, oh, sure, you can solve a 10-bit traveling salesman problem. So like that's like it's not very long on my computer, even though it's slow. It doesn't matter. But you're mentioning, hey, that actually still could be very useful in a different domain.
yeah, for sure, this is probably the first direction to explore. And these are things that So today, you look at high performance computers like supercomputers. A lot of what people are trying to do are things like that. So I think that's where we should look into. Yeah, so the thing with NP complete problems, by the way, so with NP complete problems, we don't think that quantum computers are going to give an exponential speed up. Okay, so for some of these NP complete problems, we know that quantum computers could give a speed up, but it's a quadratic speed up.
Oh.
This actually goes down to how quantum algorithms work and the fundamental. So if a quantum computer could just explore all of the different possibilities, like sometimes people describe it and say, okay, hey, here is the right path, then we can solve NP complete problems. But that's not the case because at the end of the quantum algorithm, you actually also end up with a superposition of all the results. And you don't want to measure, and you can measure only one, right? When we measure, we only measure one state. So, in order to get advantage from a quantum system, you need to do more than just explore all the different possibilities at once. So it's and so that leads to the fact that when you have a problem that has completely no structure, which is the nature of these NP-complete problems, then it's also very hard to get an advantage from a quantum computer. So we know we can get a quadratic speed up, which could be very, very useful if we had, millions of qubits that are error corrected and all that stuff. That could be amazing, practically getting a quadratic speed up for, AI right now, or this would have been amazing. So, but we're not there yet. So I think we are looking for some of those things in which you can get an exponential speed up, at least in the short term. And and some of the interesting things, I think, have to do with simulating quantum systems, other quantum systems.
I think I had fallen into that trap. I had heard, and I knew it was wrong, but I'd never heard like kind of why, which is that yeah, you just put it in the superposition, you run the traveling salesman program, and it in parallel, it parallelizes the entire algorithm, and then out the other end, pops the shortest path. Um, but I think this thing you're pointing out, I guess I don't, maybe I missed it, but it feels like it helps. Is like you can run all of those things in parallel, but then at the other end, when you go to try to find out your answer, you end up kind of back in the same problem, which is you have to keep rerunning it and keep like looking at it, and you sort of like do it, but then you have to undo it by like it's not in a form that you wanted. It is not in the sort of like
Right,
normal
exactly.
algorithm output.
Exactly. So the only way that you can actually get something from the fact that you're running all of those things in parallel is if they form what we call interference. And that's where I go back to what I said. It's very important that these amplitudes, so each path that you go has these weights, right? Like so you think about it as probability, but it's not really a probability. It's what we call probability amplitude. It's this kind of like square root of probability. It's a complex number. So it can be negative, for example. And then when those come together along this parallel computation, they interfere with each other. So that at the end, the result that you get at the end is a result of this massive interference. And if you could build the algorithm in such a way that all the wrong paths leading to the wrong computational results cancel one another, yes, it's kind of like waves in the ocean. They can flatten one another, while the path leading to the right computational result amplify one another. Then you get a speed up. This is actually how the only way we could discover quantum mechanics, right? Because we always measure at the end. So how do we know that quantum systems behave quantum, to begin with? It's because we can do, probably you've heard like the double slit experiments and things like that, where you create this interference, and that's how we know that the electron went into two slits at the same time, and so on and so forth. So yeah.
Yeah, that on that one, I mean, that's a fascinating, like not knowing anything but armchair following the kind of drama every time there's a press release from, I won't name companies, but like X company has a quantum computer that did Y thing. And then you see, on the nerdy like Hacker News or whatever, Scott Aronson's blog says like, yeah, BS, like that guy, we actually can't prove that what they did, like you could have done it classically. Like we don't know. And it's like, what, how do you have this existential crisis that like, you have this thing you're claiming as a quantum computer. You lower all these lasers into a giant liquid nitrogen, but I don't even know it's liquid nitrogen. This giant like bath of super cool, stuff, and you run this thing, and then you don't know at the end if what you did was even the thing you attempted to do. Like it's sort of this funny, like in my head, I always like, oh man, I guess I don't know enough to know, but it's a sort of a Schadenfreude, I guess, to watch other people struggle with that.
Yeah. No, and I think it's very important to clarify. It's very important for the field to clarify, that there are many things that quantum computers would not be able to do. Okay, or at least that we cannot prove. It's great by itself. We're trying to build a machine that nobody built before, and that we know can do certain things faster than classical computers, which is the craziest machine that we've built so far, right? There's like trillions of dollars that went into the development of classical computers. I think it makes sense that we will build this machine and we will test it and we will see what it can do and what it cannot do. And we know certain algorithms, like Shor algorithm, that can do stuff. But so why do we need more than that? Like, why do we need to generate a hype that is based on grounded enough? I think that we have all the right reasons to get funding to build these machines, right?
Yeah, I won't claim to know the trade-offs of marketing, but I hear you. As like an engineer,
Yeah.
I say the same thing. Like, why can't we just say truthfully the thing it does? Like, it's just pretty amazing. So we kind of talked about like a lot of really, really, really low level stuff and some of these bigger questions. And then I know we're talking about like algorithmic design, right? So people thinking, as you mentioned, like these things are amplitudes, trying to design them to cancel out. Like, are there people who have, I don't know, like the equivalent of computer science jobs today, like working in these algorithms or programming these things? Or is it's still too early? Like, are people working at that high level? And what does that kind of look like? What does it mean to kind of like program quantum computers today?
Yeah, so there are people working on it, but not enough, I would say, and I think that's actually one thing that I hope would change. But the reasons are clear. First of all, it's very hard to come up with a quantum algorithm that actually solves something faster than a classical computer on a fundamental level. Like solves it exponentially or even quadratically faster than a classical computer. That's a very hard problem, and many very smart people tried, and we have you know some examples, but very important examples. I mean, if you break the RSA tomorrow, it's huge, but it's very hard to find new ones. The other reason why I think that not enough people are trying is because we don't have the machines. Yeah, so it's a different thing. Like think about classical computers. Like think about like the you think classical computers now are what, like, I don't know, so many years, so many decades exist, and still people come up with new paradigms in not just programming but algorithms. So there are still new types of algorithms. There are new types of heuristics. There is all kinds of stuff that people come up with, but they have a big advantage. They could just try it out on the computer and see if it works, right? And it's a game changer. So that's why I think that to really have enough people trying to program new algorithms, I think that we do need more quantum computers, which is another challenge to build those things. Yeah.
So in the historical context, like you can kind of go back and read the Charles Babbage, Ada Lovelace talking about the differential engine and Ada, kind of figuring out programming of these analytical engines and trying to kind of work that out. You can talk about the ENIAC computer, or the early computers, cracking the Enigma or ENIAC, these kind of things. Like on the spectrum of like, hey, we have a theoretical thing and people are thinking, I don't want to say mathematically, but abstractly about these algorithms. So we mentioned things like Shor's algorithm or Grover's algorithm, these things that people had even before maybe the hardware was there to even try them, up to programming languages are invented. And then, as you mentioned, we keep iterating the ideas, frameworks and programming languages and paradigms and, functional versus object oriented. Like we still haven't figured out what we're doing today by any means, but there's been this sort of explosion of approaches on that same, I don't know that it maps, but in that same kind of like context, where would you say like quantum computers lay today? Like there are some, you could run some algorithms on them, but like maybe they're, like you said, not universally accessible. Where do you feel like we are on that kind of like spectrum?
Not at the very very beginning. So that was during yeah, the 90s. People had to think about these quantum algorithms completely detached from hardware. So now there are quantum computers and people can access them and you can program, but it's still very small scale. So I think that it's still hard to do that if they don't get enough, and there's a lot of noise, so you don't get the right answer. and I think we're very early, but I think yes, I think that's why it's great that we start having those quantum cloud computing services that people can log in and can try. It's not that tomorrow you're going to have like 10 million programmers trying to develop new algorithms, but I think it will increase the number of people who are trying, and it helps educating people about this. So then you kind of start having more and more people going into this field. But I think this is very early stage. Yeah.
So I have seen those before. Log on and submit your job, and does it actually run on a quantum computer, or is it like a VM? Like you're running on the like simulation of the quantum computer, slower, but like the results should be the same.
No, you can run today on a real quantum computer. So you can do that using AWS Bracket. That's their quantum computing service. IBM Quantum, Azure has quantum service. So in all of them, you can run either on a simulator or on a real machine. So you could run on a real machine as well. And then you can compare what you get with a real machine and a simulator, and you can see the noise level. And yeah, it's great.
See how good the simulator is. So I think we set up this sandwich like, a bunch of low level stuff, a little bit of the high level algorithm stuff. And then if I sort of listen to what you were saying in the beginning about where you guys kind of set up, it sort of feels like it lies in the middle there. Like the practicalness of like not figuring out the next best substance for a qubit didn't sound like, although maybe you can tell me I'm wrong. And maybe not the like, application layer stuff, actually, sort of writing those algorithms, but kind of laying in the middle. Do I kind of have the picture right? And like, what does that work end up looking like?
Yeah. So when you think about a computer, there's a stack, and there are so many layers in the stack, and there are also several abstraction layers that are required until you reach something that you can program and write algorithms with. And so quantum machines we are in those middle layers, the control layers, both hardware and control software. So the control hardware is the thing that's basically orchestrates during the runtime of the program. It orchestrates the algorithm. So that's the thing that actually runs the quantum algorithm in real time, right? Because it sequences the pulses that you send to the QPU. So you can kind of think about the QPU, think about it as the ALU in your CPU, but you need to send it all the commands and you need to do it in the right sequence. And in fact, with quantum, because of the noise, you need to do it with the right timing as well, which is something that you don't think about in classical because there is no noise. If you push me more into this direction, we can talk about the existence of time, but I don't know if you have time for that.
That's awesome. So I just looked this up. I went on AWS Bracket, and it sounds like basically you could do things that led to the disaster in the Half-Life video game for 68 cents. That's basically what I'm getting. So if you can go to AWS Bracket, it costs 30 cents to get the task up and running, and then it costs 0.0002 per shot. And in their example, that's in dollars. Their example is example two here. A researcher runs a quantum annealing program, which is I'm pretty sure what created the head crabs in Half-Life 1, on a D-Wave Advantage quantum computer in Oregon, and it cost them 68 cents. So it's just absolutely amazing that you can just do this. So folks at home, get a quantum program and spend 68 cents doing this. If nothing else, you could tell your friends. It's pretty amazing.
Yeah, it is. It is. I think very cool and pretty amazing indeed. So yeah, so going back to that control layer, so it really is the part that runs the entire quantum algorithm and sequences it. And on top of that, and so it has to have also a programming interface, which is kind of like when you think about it, the assembly level language of the quantum computer, right? And that's what we do. So we make the control system. This is classical hardware that in which we have actually designed a new type of processor, and not a quantum processor, a classical processor that gets these instructions from us, this low level quantum instructions, and then it runs the entire program on the QPU, on the quantum processor, against the quantum processor, right? So it's yeah. And then on top of that, then you have all the control software stuff because these assembly level language that I mentioned, it's talking in the language of pulses. Send this pulse to this qubit, send that pulse, change the frequency of this pulse, change the amplitude of that pulse. But we want to get to the gates, right? We want to get to program gates and algorithms. So you need to have another layer, which is called the control software layer, in which you run a bunch of complicated calibrations. So it's a graph of complicated calibrations that run programs on the control hardware and the quantum processor in order to calibrate what are the parameters of the system, or how do I perform a gate, and so on. And once you calibrated those gates, then you can create a compiler that compiles from the gate level languages down to the pulse level and down to the machine.
So if I hazard a guess that the timing and such is pretty complicated. So QPU probably, are you guys using like FPGAs, or are you like doing ASIC tape outs? Like how or if you can't share, that's fine. You can hand wave and say black box, like that's acceptable as well. Like I imagine you mentioned microwaves before. These things, like the time scales need to be very well timed, very precise. Is that roughly the kind of stuff you guys are talking about, as opposed to DSPs?
So right now we're using FPGAs to implement what I call the pulse processor. So again, that component that receives the instructions and runs them. And so currently we're implementing it with FPGAs, the biggest FPGAs in the market, and it's a bunch of FPGAs. If you want to control a relatively large QPU with tens of qubits, you would need many FPGAs. So at some point, yeah, I mean, the field will go to a dedicated ASIC to do the quantum control. Currently, it's still in the relatively early stages where you want to get the flexibility and you want to change stuff as you go, and so you do that with FPGAs.
Yeah, absolutely.
Yeah.
I mean, it sounds fascinating. So quantum machines as a company, are you guys, so it sounds like you have some of this stuff. Is it something people can try out today? Like, could I just like go to your website and like learn how to use your stuff? Or is it more like, no, you got to get in the field and it would serve some of these other things we're talking about?
Yeah, no, definitely. So at Quantum Machines, so first of all, yeah, we have our first system. It's been in the market for 3 years now. Our uniqueness, by the way, our uniqueness is that our pulse processor actually is not just running quantum operations, it's running also classical operations, and it's running, so it brings, it, it integrates classical processing into the heart of the quantum control layer. It allows you to program in a single code, which is our programming language, Qua, allows you to program the classical operations and the quantum operations, which are the pulses and measurements, in order to integrate between them. So, for example, when you try to do quantum error correction, you need to measure stuff, you need to measure your qubits during the runtime, and you need to process them classically and respond to that again with the next gates or pulses. So to do that,
Oh, it's like path dependent. Yeah, I see.
yes, you need to have feedback. So you need to have very fast real-time feedback between, sending quantum instructions, which are the pulses, measuring your qubits, which is measuring signals coming back from the QPU, processing them, doing classical processing on them, which again you want the programmer to do from the programming environment, and then the algorithm needs to understand in real time that it has to respond with the right pulse to correct an error, for example.
Oh, so when you say like controls, you mean like even control loops. So you're like controlling the
Yes.
computer, but then also control, like it's controls all the way down. I think I see what you're meaning now.
Yeah, we're running the entire sequence. So, for example, if I want to loop over a gate, I want to send gate 500 times. I write a for loop, to run this gate for 500 times. But what if I want to measure a qubit, and based on the measurement, I want to branch. So I want to say, so this is called
Oh.
mid-circuit measurements that affect the quantum circuit itself. And this is so we are the first to introduce such features into a commercial control system that allows, for example, mid-circuit measurements and branching of the algorithm. So if statement, like when you think about it, an if statement is such it's the basic thing, right? Like if x equals 0, do that. If not, do something else. That did not exist and still doesn't exist in most quantum computers today. That you cannot measure qubits and based on the results decide what you're doing next. That has to be done in the classical control system, right? Because that's the thing that measures and branches the
Yeah, you
sequence.
decide the next pulses. Yeah.
Right. So that's what we do. That's
Yeah.
that's our the key stuff that we do. And we've been selling. We have over 200 customers around the world, so we are over 130 people in the company. So yeah, it's great to be in a company that's really in the action, of everything that's happening today. So we're not sitting developing something that's going to be used in 10 years. We're really working with our customers very intensively.
Are you looking for interns, full-time people? Like, is it, I mean, how is Quantum Machines as a company to work for? I mean, this technology, I could go on like way, way longer. I have a lot more
Yeah.
questions, but I tried to be considerate here. But, are you guys, enjoying the place to work? People are liking it. You're hiring. What is it kind of like as a company culture?
So quantum machines, I think it's a fun place to come work at. We have people all around the world. Actually, we have people in the U.S., in Europe, and in Israel. So we're based in Israel, but we have people in U.S., Europe, Canada, and yeah, we are looking for both interns as well as full-time employees. We're looking for great software engineers. I know that this podcast is being listened by top-notch software people. So I think that's yeah. I mean, and I'm excited to talk here because I mean I think that we really need great people, software also hardware people that are not necessarily coming from quantum, but actually bringing their expertise into the field. It's very important that we don't let the crazy physicists try to build a quantum computer because that's not going to work without the real engineers coming and helping out. We're really looking for great people that want to learn about this. So there's a lot of stuff to do in many layers in the stack, and yeah.
Yeah, I worked briefly for some people doing laser physics, and yeah, I can relate to your. I appreciate what they do. I can't do it, but like, yeah, that sounds fascinating. Well, thank you so much for your time, Yonatan. I appreciate you coming on. This has been helpful for me. Like I learned a ton. Like I'm excited again. Like I want to go do a ton of Google searches, which I try not to do during the podcast. You hear the clacking on the keyboard. Jason's doing that for us. But you really stimulated me. So I know people out there are going to love it. Great topic. I feel like it's like it's happening. I feel like it's one of those things. It's not like an overnight thing, but like you can kind of see the changes. Setting up, and we'll see. We'll see what happens in the next few years. But like it definitely feels like a really exciting field.
Yeah, thank you so much. I mean, this was very fun to come and speak to you guys, Jason, Patrick. I mean, I appreciate that. You guys are awesome, and yeah, hope to be here maybe a few years from now when quantum computers are, up and running, solving, simulating quantum systems and other stuff. Yeah.
Yeah, I thought you'd just break crypto and then you'll just be rich. So thank you so much for your time. And thank you everyone for listening in. And as always, thanks to our listeners. We appreciate it. And I'll see you next time.
Music by Eric Barndollar.
Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.